Hello everybody and welcome to our first recorded lesson. Over the last couple of weeks you've been working on motion, you've been working on scalars and vectors, and you've been looking at how things move and how can we record and take measurements and perform calculations on working out things like speed and velocity, distance and time particularly. Today we're moving on to acceleration. So during this assignment you'll need to listen to the information on each slide, so you can actually go back on that and read it a few times if you need to. You can listen to me trying to explain it to you again a couple of times if you need to. You've always got the opportunity to pause it, go back and do it again. There will be tasks to do as we go along. They'll be on the Word document that's been put onto Teams with this, or if it's been sent home to you, then obviously it would have been in part of the package that came back with you. Now, the only thing to remember is that when you see that little red box come up on the slides at the bottom, that's time to pause the video. I'll give you a second between me talking to allow you to do that, and then you can complete the Word document. Once you come back to it, if you think you've done that okay and you're quite happy with what you've done, you can carry on listening to the recording. If you're not quite sure on a few bits, then obviously you've got the opportunity to go back and listen to a few things again. So, first of all, before we start talking about acceleration, now a lot of you have been handing in work recently on these sorts of motion graphs, and you've been doing really well, particularly on the distance time graphs. You've been doing particularly well. There's just a couple of things I wanted to point out on velocity time graphs which have been tripping a couple of you up. So if we look here at the graph A, the velocity is on the y-axis and the time is on the x-axis. That's perfectly normal and everyone seems to have picked up on that one. Now the thing that seems to be confusing everyone is the difference between A and B. So if you look at A, at the moment the line that's being recorded is on zero velocity. It's not moved up that y-axis at all. Okay, if there's no velocity, there's no speed, there's no movement. Okay, so the object is stationary. If the line was up here and coming across, it wouldn't be stationary, it would have a constant speed or a constant velocity, because let's say for example that was 20, it would be travelling at 20 for the whole period of time that recording was being taken, much like this graph over here. So this graph here is showing constant speed. The other two graphs we seem to be quite happy with. We've got this one here which is showing constant acceleration. That's because the velocity is increasing, and this one here is showing that the velocity is decreasing. So as you move across the time, the velocity is actually decreasing, becoming less. Okay, so if you're still not sure about that, it's worth popping me a quick email. It's worth popping something on Teams, because it's really important we get this. And most of you have been absolutely fine with all of it, except for the difference here between constant speed and being stationary. And you need to remember, if there's no velocity, then it's stationary. Okay, what I'd like you to do now is pause the video and have a go at the four that are on the worksheet at the top. We've just talked it through, so again, if you're still not sure, re-listen to this again, have another go, and hopefully we'll have 4 correct answers in the next minute or so. Okay, moving on to today's lesson then. We are going to talk today a little bit about acceleration. I think most people have got a decent concept of what acceleration is. So, acceleration, in a simple definition, is a measure of how quickly the velocity of an object changes. Okay, so if it's going very slowly and then suddenly starts being moving very quickly, then that's obviously got a really rapid and large acceleration. If it's moving like a snail and it goes from snail speed to stop, then obviously there will be less acceleration. We would say that was a smaller acceleration. So acceleration of an object, measure of how quickly its velocity changes. So if I look at this train here, it accelerates in a straight line from rest. As it does so, its velocity increases. And acceleration is a measure of how much that velocity is increased. On the flip side of that, we can also have a negative acceleration, which we call a deceleration, normally through braking of an object, such as a motor vehicle of some sort, and this motorbike that's on here, and that's associated with a slowing down or a decrease in the velocity of an object. So, as per normal, like it or not, there is an equation to go with that, and it's hopefully quite a nice simple one. So we're looking at that's the size of the change in velocity, and then we're dividing that by how long that change has taken. So an object might lose a large velocity, so it might go from 100 miles an hour to 0 miles an hour, but it might do that over a period of 10 minutes, and in which case the velocity and the change in velocity, so the deceleration, is quite slow. Now it might go from 20 miles an hour to 0 miles an hour, but do that in a matter of seconds, and in which case the deceleration of that would be much larger. So acceleration equals change in velocity over time taken. Okay, and remember that it can be negative as well, so the change in velocity might be a negative value, which would give your acceleration overall a negative value as well. One thing to notice when we're looking at the units on this, because we're dividing meters per second by second, we're actually dividing a period of time over a period of time. So what you actually end up with here is like it says here, you've got meters per second. So if you've got meters per second, rather than having MSS, we describe that as being meters per second squared. So when we're looking at acceleration, the units that I'd like to see is always meters per second squared. Okay, so velocity meters per second, acceleration meters per second squared, and it's because you've got these two s's. Okay, so two s's, s squared. Okay, so an example: my car goes from 0 to 30 meters per second. Sorry, so it's got a change in velocity of 30 meters per second. I'll put that in red here so we can see where that goes in a minute. This takes 5 seconds to occur. So I want you to calculate the car's acceleration, and hopefully you've got a few things going on in your head already. So our change in velocity, 0 to 30, that change is 30 meters per second. And it's taken 5 seconds for that to take place. So we're going to look at it nice and simply, 30 divided by 5, and our acceleration is going to be 6 meters per second, and remember it's 6 meters per second squared. Okay. What I would like you to do now for me, please, is pause the video, have a go at the first section on the worksheet, and then when you're ready, come back to the video. Okay, so this change in velocity, the question might not give you the change in velocity. It might not tell you that the change in velocity is 30 meters per second, 100 meters per second, whatever it might be. You might actually have to calculate that, and it's nice and simple. Okay, so when you see this equation, please don't panic. Okay, there are more letters involved in this equation, so it looks like there's more to do, and there is a little bit more, but there's nothing too scary. So if we look, we've still got the same things here. We've still got acceleration, we've still got time, but this time we're doing a very small calculation to work out the change in velocity. And the way we do that is to have our final velocity take away our initial velocity, so our starting velocity if you like, and that will give us our change. Okay? So it's really, really important that you get those two letters the right way around. So it has to be your final velocity take away your initial velocity. And that's regardless of which of those two values is biggest, it always has to be v minus u. So final velocity minus initial velocity. Okay, so one work through here, we've got Mikey accelerating from a standstill to 50 meters per second, and that took place over 25 seconds. Okay, so what is acceleration? So the first thing we need to do, we just have a look at our formula. So we're trying to work out acceleration, so we don't know that at the moment. We're hopefully going to have the rest of these values to be able to work it out. And if you look at the colour coding that's gone on here, we've got a final velocity, which is the velocity that he finished at, or the recording was finished at. We've got the yellow one here, which is standstill. So we're going to look at 0 for that one. He was static to start with. And then we've got 25 seconds that took place over. Okay, so put those values in, 50 minus 0, our change in velocity will be 50. And that's taken over 25 seconds. So what we've got, with my apologies, is 2 meters per second, and again it's squared. Okay, one more. I've got Mr. Dennis Smith, we've got his Harley, he wishes, accelerating up from 15 meters per second to 50 meters per second. It takes him 8 seconds to do this. So what is the acceleration? So his initial, so starting point was 15, his final was 50. So remember, we need to put those in the formula the right way around. So it's going to be 50 minus 15, his final minus his initial, and we divide that by time. So 50 minus 15, that should be an 8, not a 7, okay, divided by the amount of time it took for that to take place, okay, and then we've got 35 divided by 7, or as it should be 8 in that question, which would give you 5 meters per second squared. My apologies for the error in that question. Okay, so again, I'd like to pause now, have a go at the worksheet labeled task 2. If you need to, go back over slides 7 and 8, and then obviously when you're ready to carry on with the presentation, come back and press play. Okay, just as we said at the start of the video, we can also have a negative acceleration. So we've got possible that things might be slowing down. So a car travels from 30 meters per second to stationary, it takes it 40 seconds to do so. This time we're going to ask what is the acceleration. Okay, because it's gone from 30 meters per second to stationary, it means it's slowed down. So we're actually looking at a deceleration or a negative acceleration. But we need to put our values in the formula in the same order as we have done before. So stationary, 0, 30 was the final velocity, the initial velocity. So we've actually lost 30 meters per second in terms of our speed, and that took 40 seconds to do it. So this time we've actually got a negative acceleration of minus 0.75 meters per second squared. The car is slowing down. Okay, so if acceleration is negative value, it means it's slowing down. Now, hopefully in your exam at foundation level, you won't really need to do too much moving around with this formula. So it looks a little bit more complicated than normal because we've got this v minus u on the top bit, but then we've got the acceleration and the time. So remember, if we covered up that acceleration, the a in the bottom corner, we've got v minus u over t. So final velocity minus initial velocity divided by time. Okay, so remember, use your finger, cover up the bit that you are trying to work out, okay, which will normally be acceleration, but it could be something else. Cover that bit up and then use the other bits to work out your answers. Okay, so have a go at the tasks labelled on task 3 on the worksheet. So we touched on this at the start. We looked at velocity time graphs. You can actually do the similar sort of maths that you did on the distance time graphs with a velocity time graph to actually calculate acceleration. And again, we can use the gradient of the line to do that. So a very, very steep line, as in A, high here. A very, very steep line means the acceleration is quicker because the velocity is changing quicker. This one at the bottom, velocity is changing more slowly over that same period of time, so it's actually got a much smaller acceleration. Worked out in the same way, you need to know the gradient of a line. So you're looking at that change in velocity or change in speed. It's the same thing in this case. Okay, so if we look at this, the change in speed is 20. It's gone from 0 to 20 over that period of time. So that goes into the top, 20 minus 0. And then the change in speed, the change in time even is 5. So it took 5 seconds for the speed to change by 20. So if we put all that in all together, you'll be able to calculate the gradient of the line and therefore the acceleration of that object. Okay, so complete task 4 on your worksheet. What I'd like you to do is work out the gradient of each one of these lines. So this one here, for example, A, over this 3-second period, the velocity has changed by 12. Okay, the one that's going to be slightly more difficult is C. So this period here, you've got 5 to 8, so that's a 3-second period, and your velocity has only changed this time by, 3. Okay, so you can do your maths on that. Right at the end of this presentation is the answers to this part of the graph, and I'd like you to self-assess your answers on that last slide when you get to it towards the end. And if you're not right, and you're not sure why you're not right, come back and have another look at this, and if you're still not there, again, drop me a quick email. Okay, pause the video now, and if you could complete that. Last little bit we're going to look at today is something called terminal velocity. Now, objects have a maximum speed, okay? And the reason they have a maximum speed is because, I said before, our forces act in opposite directions. So if, for example, in the example we're going to look at in a moment is a parachute jumper, that parachute jumper will not continue to accelerate indefinitely. Okay, they will actually reach their top speed, and we call that top speed a terminal velocity. And if we look at this graph here, we can see what's happening. Initially, the acceleration is very, very quick. Okay, but over the period of time, the acceleration slows, and eventually there is no more acceleration. So we stay at this continuous velocity, and that period there, as we said, is our terminal velocity. If you want to, there are a couple of video clips here that might help you out. So if you want to listen to me first and then you get to the end of that and you're not quite sure, please go come back and have a look at these videos, or you can look at them now, whichever you prefer. So we're going to use an example of a parachute jumper. When this object starts to fall, when he falls out of the plane, he's going to accelerate very, very quickly. So he's going to go from 0 speed to a high speed in a very short period of time. And that's because the only force that's acting on is gravity. And gravity is an acceleration. So it's actually pulling him down, increasing his velocity. On the Earth, in our atmosphere, we have air, as we're all aware. And that air resistance is actually going to oppose the force of his movement. So to start with, this one here, as he's just come out of the plane, has got a really big force of gravity compared to the air resistance that's acting in the opposite direction. As he continues to fall, it gets faster and faster, that air resistance becomes greater. And eventually, you'll see here that as he continues to fall faster and faster, he gets to a point where the air resistance acting on him is just as strong as the force of gravity that's pulling him down. And we say at that point that he's reached his terminal velocity. So he's not going to go any faster. He might be going very, very fast, but he's not going to be increasing his speed anymore. And obviously, as you're aware, when he pulls his parachute, the forces on him will change again. So this force here will actually become even bigger, there's air resistance, and that will actually start to slow him down. So when the two forces become equal, as we've said before with our force diagrams, we say the resultant force is 0. So the forces acting in each direction are the same, and in that case, he will be moving at a constant speed. Okay. Please remember, it has not stopped. Okay, it's just continuing to move at the same speed in this case. So, last thing to remember, if we there are quite a couple of nice YouTube clips on this actually. If you are in a vacuum, so there is no air, there's no air resistance around you, the object would continue to accelerate and would continue to fall. But those objects will fall at the same speed, and that's because the force of gravity is acting the same upon both of them. Okay, so if this astronaut did drop those on the moon, he would find that they'd both fall, and if he dropped them from a higher height, he would notice that acceleration continued until they hit the floor. Different to on Earth where there's air resistance slowing those objects down. Okay, what I'd like to do now, please, is complete task 5 on your worksheet. Okay, it's all about terminal velocity. There's a couple of gap fills on there, and there's a couple of questions that I'd like you to have a go at. So you can pause your video now, please, and have a go at those. Okay, last bit, as I said, we've got the answers here to the part on the velocity time graph that we looked at before in terms of calculating those gradients. What I'd like you to do is check your answers. If you're not right on them for any reason, please do come back to me. So that concludes our video on acceleration for today. Please let me know how you got on. I'd look forward to receiving the Word document from you very soon. You don't need to return the PowerPoint to me at all, just the Word document. If it's easier, as always, email it to me, take pictures of it and email them to me, attach it to Teams, whatever you're finding the easiest at the moment. And say, any problems, give me a shout. Thank you for listening. Hope you're all well.